Good afternoon, everybody. Thank you for coming to this session. My name is Jose Blakely. I am architect in the SQL Server Engine team. I've been with Microsoft for about 14 years, and I've had the privilege to work in multiple releases of SQL Server, starting from SQL 7.0, 2000, 2005, and more recently, 2008. And I'm very happy to be here to talk to you about developing large-scale web applications and services. I'll start by putting this presentation in the context of the theme for PDC. Yesterday at the keynote, Bob Muglia talked about this paradigm of Windows Azure Services Platform as the platform for building this next generation class of applications on the cloud, and how this new platform complements our traditional on-premises platform, where SQL Server, Windows Server, and all our offerings have been providing value for you all these years. Yesterday, David Campbell talked about how you program against SQL Server services, and he did a fantastic job of showing all the scenarios where you can use this new platform that we are offering to you to build this next generation of applications. Today, we are going to be talking here about the left-hand side of this presentation. So for all of you who are faced with the challenges of building very large-scale applications, you need to be able to apply careful design patterns to be able to make your applications scale without limit. And so that's the focus of our presentation here today. The SQL Server Data Platform has the philosophy from its origins, all the way from 7.0, to be able to solve the majority of the scalability challenges for you automatically. And we've been able to achieve this for a vast majority of applications. Over 90% of the scalability problems are solved automatically by the platform, with things like self-tuning, query optimization, self-configuration, and self-management. Indeed, in SQL 2008, we have declarative policy management, which allows you to manage your installation based on SLAs. But there is a remaining few percentage of applications which require very careful design in order to be able to make them scale without limits. And it requires having a good knowledge of the capabilities of the relational system, as well as the hardware on which your application is going to run. And that's the focus of our application today. How do you build these super high-scale applications by working through all the design issues that are involved in there? The takeaways for this talk are that scalability requires careful design and best practices. As we learn about these design patterns, we capture them, we learn about them, and we try to codify them into the platform. And we go again, we discover new patterns, we understand them, and we try to bring them into the platform so that fewer percent of applications can be handled automatically over time. Now, we're going to be talking about specific design patterns for scalability, for unlimited scalability. And the key here is that we are really trying to solve complex problems. And to solve complex problems, we need to basically divide and conquer the problem by looking at ways to partition the problems into independent units that can work and scale independently. So we're going to be talking about functional partitioning of the application, data partitioning, and the role of transactions in this world. Once we decide to partition your application into functions, if you have operations of your application that require communication about the various functions, you can decide to apply distributed transactions, or you can rely on a reliable messaging infrastructure to be able to communicate these various functions. Distributed transactions is a pattern that is not very scalable. Okay? It has its limits. So we are trying to develop these designs where the key to infinite or unlimited scalability is to try to guarantee locality of operations and transactions. So we're going to be talking about how we can do that in your designs. And then to prove that these designs really work, we're going to be telling you about 3 real-life case studies of large-scale applications. I'll be talking about a major US stock exchange customer that we had and how we built that application. I'm going to be joined later on during the talk by Hala Al-Adwan, Vice President for Data at MySpace.com, who's going to tell us about how she has built this massively scaled system. And then we're going to be joined by Roger Doherty, Technical Evangelist at Microsoft, who's going to tell us how he built one of the monitoring services for the MSN Olympics website that was in operation this last summer. So, first of all, let's talk about SQL Server, the data platform. So yesterday, David Campbell did a fantastic job in showing the vision of SQL Server. Our vision is to be able to manage all your data, any place, any type, any scale. And in order to build that, this is our aspiration and our vision. This vision is based on 4 pillars: enterprise data platform, beyond relational, dynamic development, and pervasive insight. Now, in SQL Server 2008, we are delivering on this vision by providing capabilities and contributing to each one of these pillars. In the area of enterprise data platform, we have a trusted, reliable platform. We have done tremendous progress in query optimization and performance. We have resource governors, a way to control CPU and memory resources, to control your workloads and manage your system better. And we have also added declarative policy management tools, which enable you to define policies to manage your system as a function of your SLAs. In the area of beyond relational, we want to allow you to read and write all types of data. We understand that in this generation, data is more than numbers and strings. You have file data, XML, spatial, all kinds of semi-structured data. So we want to give you capabilities and build a platform for you that allows you to handle all these different types of data. So in SQL 2008, we've been able to add support for spatial data types. We have a new extension to develop capabilities to allow you to provide file stream support so that you can have your video and your images and your multimedia data stored and with the streaming performance that the operating system can deliver for you. And we have also added the ability to define sparse columns into your tables so that when you have large applications that perhaps are multi-tenant type of applications that rely on provisioning a universal table that can handle all kinds of objects and schemas, you can do it and enjoy all the power of the relational system. In the area of dynamic development, we've been making tremendous investments in the area of just improving your productivity by building an entity model, the EDM and the entity framework, which allows you to speed up the challenge of mapping the world of tables to the world of objects where your application lives. We also have made significant improvements in the area of synchronization. And yesterday, Dave also gave a demo of how synchronization allows you to build these disconnected or occasionally connected applications. In the area of pervasive insight, we've been able to improve and manage all your data by adding capabilities in integration services, our ETL tools that allow you to integrate all the data in your organization. And also by adding capabilities in our reporting services and analysis services so that you can deliver value for your data to a broad class of customers. So moving on, to establish a common ground, let's talk about basic concepts. This is our assumption and focus for this talk. We're going to be talking about workload types briefly, just to set the stage well in the next slide. But our talk is primarily on OLTP scale-out, the kinds of applications that have those characteristics, and we will talk about that. So when we're talking about large-scale applications, we need to understand the dimensions of a scale. There are many challenges in building these applications. Some of them require to manage hundreds of thousands of transactions per second. Some of them require handling hundreds of thousands of concurrent users. Some of them require handling massive amounts of data in the hundreds of terabytes to petabytes. And each one of those dimensions brings different kinds of challenges for us. But what we're doing here is we're looking at determining what are the patterns, the design patterns that can lead to unlimited scale. Okay? So just to give away the key here is that really we need to, our goal is to be able to maintain locality as much as we can, both of transactions and operations. So when we have data items, we want to make sure that all the operations on the data items or entities, which I'll introduce later on, are always residing on a single node. And transactions never span more than one node. And we'll talk about some of those things in more detail. So, and we want to be able to maintain that locality in the presence of data growth. So as data grows, data repartitions across your infrastructure, across the various machines and nodes in your center. And you want to make sure that as that data grows, those operations and transactions over your entities remain local. Okay? Briefly, workload types. There is online transaction processing and data warehousing. In online transaction processing, we typically have a balanced ratio of reads to writes, typically in the order of 60% reads, 40% writes. They are characterized by fine-grained inserts and updates. Okay? We typically want to be able to handle high transaction throughput in the orders of tens of thousands of transactions per second. Some transactions, they are really very small. And by small, I mean they touch a few tables, 1 to 3. Once transactions start touching more than 3 tables, you start getting into complex queries, and that at some point becomes a bottleneck. So there is always this trend towards trying to keep your operations and your entities scoped to a few tables. And the sizes of these databases are relatively small, in the order of a few terabytes. For data warehousing, the read-to-write ratio is different. It's usually 90% reads versus 10% writes, thereabouts. There is few updates in place. Most of the stuff is high-volume bulk insert, so we want to be able to guarantee that you can upload terabytes of data per day very fast, while your concurrent query workload is operating. Usually we have schemas that have the shape of a snowflake or a star schema, and the queries executing on these schemas represent complex queries involving joins and filters and aggregations. And the volumes of data usually involved here are in the tens to hundreds of terabytes. So that's about, when I talk about OLTP and data warehousing, those are the type of characteristics of workloads that I'm talking about. Now, in the area of OLTP, there is a scale-up and a scale-out. Briefly, a scale-up is, for the most part, a solved problem. And this is why. Here's an example of the performance of SQL Server over the last 12, 13 years. And this graph represents the behavior of SQL Server. The TPCC benchmark represents the performance per socket. And as you can see, as the hardware has evolved from single core, dual core, to quad cores today, we've been able to pretty much ride and keep up with Moore's law in terms of the capacity of transactional throughput that we can deliver per CPU socket. Now, if you look at the total transaction throughput delivered by commodity standard servers, and these are not the highest end of the servers that you could provision in your application, we can achieve in the order of 1 million transactions per minute, which is a lot of capacity to be able to handle a lot of applications. If we look at package applications, and we take SAP as an example of a package application, again, there is enough capacity to handle most of the SAP customers. About 98% of the customers can be handled with this capacity that we have over here. And this graph shows how SQL Server over the last 10 years, every time we've had a different generation of a CPU, we've been able to at least double the throughput of the SAP SD benchmark. And so today we can, in this, again, in the standard servers, in the order of $35,000, a volume 34,000 transactions. And this is, for example, Microsoft requires half of that capacity to be able to run the entire company. So now in the area of data warehousing, SQL Server 2008 delivers an out-of-the-box scalable system for databases in the order of tens of terabytes. And we have features like data compression, star join and bitmap filter optimizations, parallel query processing over partition tables, minimally logged inserts, and merge operations. These are upserts, or basically operations that allow you to either insert or update in place your system. There is a resource governor that allows you to define classes of users so that you can define quotas for utilization of CPU and memory, and so that you can keep your system from runaway queries and from query workloads that may actually monopolize your resources. We've also been able to build many successful applications in the 10 to hundreds of terabytes, and they are running today. And the names of the companies and institutions that I have there are proof of this. Now, we are also building an out-of-the-box scale solution for the hundreds of terabytes. And this is part of a recent acquisition we made of Data Allegro. And so we are making progress in trying to automate the scalability of this category of workloads as we roll out new SKUs and new versions of the product. So we will not talk about data warehousing anymore in this talk. We'll now concentrate on scale-out patterns. So what are these design patterns? Well, here's an example of a typical commerce service application. And usually in this kind of an application, you can identify your product catalog as a read-only reference piece of data. You may have it replicated to be able to increase your high availability. You may have the need to handle shopping baskets. And you may partition those shopping baskets. You may have customer data, again, which you can partition so that you can scale to large numbers of customers. And you can have order processing. Now, when you are able to basically divide and partition this kind of a complex application into its functional pieces, each one of those pieces can be handled independently, and you can scale them without, you have more freedom to scale these sections of the application. So here's the first case study. This is the work we did with a major US stock exchange. The requirements basically is a stock trading application, a trading and ordering matching system. The requirements were to be able to handle a volume of over 100,000 trades per second. And these are complex financial transactions per second. These are not simple transactions like TPCC. Usually they are multi-step. They are heavier weight than what we can measure with TPCC. The requirements of the application require a very fast turnaround in the order of 16 to 20 milliseconds for the entire transaction to take place. The application also requires smart design to be able to handle high availability and fault tolerance. But we are not going to be talking about high availability and disaster recovery of this app in this talk. We are just going to concentrate on the transaction throughput. So the design concepts that we used here were we basically partitioned the application into its functional pieces. There was a message router, which was the entry point into the system, which handled all the requests. And by looking at the type of trade, the origin of the trade, tried to route the application to the right order maker. The order maker then recorded the bids and the asks of these transactions and then sent them to matching engines, which were able to execute finally the transaction. And then throughout the entire operation of the system, it was necessary to keep a journaling system, which was required for history, regulatory compliance, and also as a way to maintain high availability in the case of failures. The system used data partition heavily, aligned with the functional partitioning of the app. And it used messages for communicating across the various functions of the app. So we went through 3 iterations in the design of this system. In the first iteration, We identify the various functional pieces of the app. The access series is really the message routing, the order maker, and the matching engine. But we built everything on a centralized database system where all the functions were in a single database. That was a scale-up option. It had the limits of performance of the scale-up solution, but it was easy to develop. Single instance, single database. The kind of throughput we were able to achieve with that design was 50,000 trades per second. Now, the first thing that we tried to do then was to separate the journaling function of the system. This is the logging capability, the historical record of every single operation throughout the system. That wasn't an operation that was central to the trading, but it was super important to be able to not lose any single of those trades throughout the life of the trade in the system. With that split, the system was able to handle 70,000 trades per second, okay, and required 2 instances, 2 databases, and so on. Now, in the third iteration, we basically aligned the data partitioning with the functional partitioning. And for that, we were able to achieve a volume of a volume of 125 transactions per second for the system. And the capacity of this system was actually is one where we believe we can handle twice this capacity. But now we have a lot of freedom to be able to scale every single functional piece independently. And so that's an example of how, in this particular application, this pattern was applied. Now, once we start separating these functional pieces, it is important to be able to communicate the operations on each one of these functional pieces through a reliable messaging capability. So how can we achieve this? The goal of reliable message semantics is to provide an exactly once in order delivery of messages across the system. Now, if you are rolling your own system, you can build your own messaging capability. But to build these kinds of systems is really hard because you have to guarantee that the recording of the sending is durable, that the acknowledgement that the message has been received is also durable, and that the match between send and receives is paired up reliably. So you can roll your own building on top of any communication infrastructure you may choose, or you can use a built-in one, like Service Broker. So Service Broker is SQL Server's messaging capability. It has a communication infrastructure in the database that allows for server-to-server communication, reliable server-to-server communication. You can define concepts like dialogues and conversations that allowed these pairings of message interaction to operate. The reliability of the messaging is achieved because the queues are tables, and when a message is received, it's an insert into the table. And so all the transactional semantics that the database offers are guaranteed in this messaging service. It provides exactly once in order semantics, and it allows you to have support for large messages. When you have messages that are really hundreds of megabytes, the system is able to optimize for the sending of fragments and guarantee maintain the delivery guarantees over these large messages. There are also activation services so that you can customize what happens with your message when you receive it. So when a message is sent or received, there is an opportunity to actually write code that is activated upon those events. And that code can be written either in T-SQL or in CLR.NET. And in the next two case studies, both Roger and Hala are going to tell us about how they are using Service Broker in their applications. Okay, Roger.
Thanks, Jose. Good afternoon, everybody. My name is Roger Delwordy. I'm with DPE, which is the division that brings you the PDC, so I hope you guys are having a great conference. First question, though, are there any Dodgers fans in the room? Any Dodgers fans? Yeah? No? Okay, good. If you're a Dodgers fan, you can go now, okay? Earlier this summer, we encountered a very interesting project where the Scott Guthrie and the Silverlight team and NBC got together to host the largest on-demand broadcast event in history on the web with the 2008 Summer Olympics. It's a pretty ambitious project. We delivered streaming video for basically every minute of every sporting event at the games. There were 2,200 hours of live coverage and over 3,000 hours of on-demand coverage associated with the event, encompassing over 70 million video streams for 600 million minutes of video. So this was a massive application. The site really was designed to drive a superior user experience, which I'll talk a little bit about in the demo, with things like adaptive streaming support, 16:9 viewing, picture-in-picture, and a variety of other interesting interactive capabilities that really made the user experience at NBCOlympics.com one that really kept users coming back and extended their session to some pretty impressive results. This system was really designed to add value to their television broadcast coverage of the Olympic Games, not to supplant it. So this was a very interesting synergy between a traditional media like television and online media. And it worked very well. They found that many of their users were using both mediums to experience the Summer Olympic Games. The project was monetized using pre-roll video advertising, and this is the the ad that you get when you kick off a video. You get maybe a 25-second advertisement before you actually get your video content delivered, and that's how they paid the bills. The system overall was a major success. It was a record-setting average 27-minute session. So for any of you that are involved in any kind of web-based applications, keeping a user's eyeballs on your content for anything more than a couple of minutes is a major achievement. And through some ratings agencies, we found that the average experience, Olympics experience on other sites was around 3 minutes. So it's really important. We get so caught up in the bits and bytes and the plumbing of building these massive scale web applications. You can have the best plumbing in the world and have a really poor user experience, and you lose, right? So they go hand in hand, and that's a big part of what we talk about with software plus services. So we had a lot of challenges with this system, and this is where I got involved. We had a variety of monitoring solutions that monitored our back-end content delivery networks. They monitored our ratings. They monitored everything but what was actually happening at the client as part of the client user experience. So what we decided to do was build a real-time logging service to track the client quality of service and the usage patterns of clients that were working with content on the site. In Silverlight 2.0, we were able to build some instrumentation for this logging capability, and there were some basic things that we needed to achieve with that instrumentation to make sure that it scaled. First of all, it needed to throttle. So, for example, if a particular client was experiencing a very, very high rate of the same type of error, we would stop sending the errors, right? We would throttle back. No need to send the same error 42,000 times, right? The first 15 times, probably got it, right? We wanted to avoid chattiness, so we spent a lot of time kind of compressing the stream and the web services call down to the smallest amount possible, so that we weren't soaking up a lot of bandwidth on the wire with the monitoring. It couldn't block the client. So if for some reason the logging service on the back end was unavailable, that should be completely transparent to the user. They should never know that there was a logging service on the back end of this thing. And it must permit dynamic updates. So one really cool feature of Silverlight is the ability to deploy new builds for Silverlight-based applications and get your code out there dynamically in stream. So we had a couple of examples where we needed to collect different types of information. Like halfway through the project, we decided to start tracking video start events, and we were able to kind of substitute that in, and have those bits dynamically deployed out there to all the users. On the back end, the logging service itself needed to be able to handle an unpredictable load. We were expecting anywhere from, anywhere up to about 500,000 concurrent users at any given time. And so we really needed to be able to handle that type of load. And we need to keep that service available and very highly responsive. We didn't want to lose any data. We figured that there was a gold mine of forensic information in there and usage patterns. So we didn't want to have to throw away any data if we could possibly avoid it. So we wanted to make sure that if some messages got sent up to the logging service, that it would eventually make it into our system. We wanted to be able to provide near real-time reporting and analytics. This system was to serve as a kind of an early warning system of problems that were out there. Maybe, say, and there were several that occurred, actually. In one case, we had some hackers in Germany who decided to write some apps to consume a bunch of streams. And we started getting some geofencing errors that were exposed by the system. We were able to go and reroute that traffic and shut that attack down. There was another circumstance where we had a ton of media failures occurring due to a server in Texas who, in the data center, whose time was not set correctly. So it was like, I don't know, 2 days out of whack or something like that. So a lot of the streaming events were failing just off that one server. And through this system, we were able to kind of figure out that that was what was happening and go get that problem addressed so that the quality of service wasn't compromised for our users. So this was really, again, an early warning system that we got at the client. Also, we need to be able to permit dynamic updates. If we were going to be collecting new information, our back-end logging infrastructure had to kind of gracefully respond to that and allow us to get more information into the system. And probably the most interesting statistic, myself and one other developer, Eric Schmidt, who's a director-level guy at Microsoft, who runs our media and advertising initiatives group. The two of us built this system in less than 2 weeks, and we hosted it with a partner, ORCS, who was extremely responsive and really helped us get the system up and running very, very quickly. So, time to market was fast, and I know all you are smart developers. This stuff can be done in a short period of time if you need to. So to talk a little bit about the design of the logging service, basically the way it works is the client constructs a message and calls our logging service, which is a Windows Communication Foundation-based service. So it's basically a SOAP call to an IIS-7 server, and that's where the message gets passed. Then the logging service calls a send message stored procedure with the incoming message. Nothing fancy here. It's just a WCF app calling a local stored procedure on a local instance of SQL Server running on our web server. Okay? So that's the only connection that gets made to a database from a client is through this web service, a local call to basically a local queue on a local instance of SQL Server. And that could have been SQL Express if we wanted it to be. The send message stored procedure starts up a dialogue between our initiator and target service and then sends the message. So here, Jose was talking about the fact that there are defined interfaces and server communication protocols. The way that's exposed in Service Broker is through a service concept. So you have these services that you wire together, and they use kind of contracts of messages to communicate with each other. Next up, the initiator service stores that message in a transmission queue until Service Broker can forward it to the target service endpoint. If the target service endpoint is down, if it's unavailable, it sits in the transmission queue until it comes up. So that gave us the ability to actually take down our data tier and do modifications without losing any data. The message is just queued up in our web front ends. And then once we brought the data tier back online, the system would eventually catch up and dequeue all of those messages. So once the message is at the target service in the data tier, it gets in queued there as well. So, as I mentioned, we could have up to 500,000 concurrent users on this thing. So we might not be able to keep up with our peak load. So we wanted to make sure that we didn't lose any data. So we use Service Broker back there as well. At that point, an activation stored procedure fires. It dequeues the message, calls a SQL CLR deserialization procedure, which is a really fast way of shredding XML inside the database server, and then inserts it into our raw log table. And that's basically the path of a message through the system. So that's a conceptual framework for how the logging service works. The messages were really simple. We stuck with a very loosely coupled message schema of basically name-value pairs. So you can see an example of the schema here. NVC stands for name-value collection. The NVP is a name-value pair. We then use metadata to map those name-value pairs to particular columns in our database. In this case, I'm showing the name attribute, but that was an optional attribute. So when we actually went into production and we went out of debug mode, we stopped using that name attribute to cut down on the amount of, on the size of the overall message and cut down on our traffic. Okay? So the pros of that allows for addition of new attributes. That actually happened. Attribute 25 there, the server log time, we added that after the fact. This was a, you never get these things right on the first crack, right? It's always an iterative process, just like Jose was talking about. One of the things that we relied on was that the client time would be accurate. That's incorrect. We had clients that showed their time as being, January 1st of 1753, stuff like that. So what we had to do was grab the time that the message actually arrived at our web server front end, the server log time, as the time that the event occurred, right? We had to sub that in later as another attribute. So we just added it as attribute number 25. We didn't have to create a brand new message schema and all of that kind of stuff, right? The cons are, this is like hardwiring metadata from messages to to columns in a table. And it sounds like a simple enough approach, but if you get enough attributes and a complex enough message structure, this begins to break down, right? So for a very simple logging scenario, this worked just fine, okay? The message is serialized at the client into XML. It's deserialized once at the server in our data tier using the SQL CLR, using high-performance XML serialization routines. Okay? That's really key. If you're going to be working with messages in your data tier, you have to make sure that you don't get overwhelmed with CPU activity associated with parsing, validation, shredding, all of those kind of things. I worked on the UDDI project. Anybody remember UDDI? Yeah, a couple of you. Anyway, UDDI did a lot of XML shredding in its first release. We did it all in the database using Transact SQL. And then I was really shocked when we had 100% CPU utilization with just very minimal load. You have to be really careful with how you do it. This is the fastest and most efficient way to shred XML inside the database. We used a simple fire and forget message pattern, and we used what we call conversation handle pooling. Just like you do connection pooling for synchronous connections, there are similar types of things inside Service Broker that you can benefit from using pooling. You have to write a little bit of extra code to implement that pooling logic, but it pays off big time if you're under a massive load. So the physical architecture at our partner ORCS looked like this. Our clients, our Silverlight clients out there, there were millions of them. 60% were Internet Explorer, 40% were other, Mozilla, Linux, Mac, etc. We had an IP load, a redundant pair IP load balancer. The peak activity at those we saw was about 5.4 million hits. We had 40 million unique users come in through the life of the games, logging messages to this system. The IP load balancer would then route a request to one of our 15 front-end web servers, which were running the code that I just walked you through. And then on the back end, in our data tier, we had a single SQL Server instance with service broker queue where our raw log table would get materialized. And finally, on the back end, every 5 minutes, we would run an integration services package that would pull the latest log data, transform it, and make it available in a reporting and analytics system. So the basic end-to-end scope of this thing was to collect the information, submit it up to the logging service, log the information, transform it into something that was useful from an analytical perspective, do some reporting, respond to the scenarios that we were encountering as a part of the reporting process, and then start it all over again. And this system was used live by the operations team at 30 Rock to diagnose many of the issues that I discussed, and also to get a feel for what was the popular content, et cetera, that was occurring during the games. So just to give you a quick demo of what this looks like in code. How am I doing on time, Jose?
They're getting close.
Getting close. How many minutes do I have left?
About 2, 3.
Okay, I can do it in 3 minutes. No problem. So what you're looking at here is a VPC where I have basically a test version of this system deployed. And I've got 2 instances on my VPC. I've got my main instance called Miami, which is where my log table is going to reside. And then I have a queuing instance as well. So let's do a little cleanup here first and reset the demo. And then I'm going to connect up, and I'm going to disable activation on my service broker queue. This is going to suspend message processing in my data tier. And I'm doing this so that we can track the progress of the message through the system. OK, so now we're going to go up to the web front end, and we're going to construct a message. So I've got some variables in here. I'm just concatenating together a big string, which is my XML instance with my test message. Okay? And we're going to build this message up and submit it to my web front end. And it will be stored in the initiator's transmission queue. So that happens through a simple stored procedure call here, send message. So we'll go ahead and fire that off. OK. So that looks like it worked. Now, just to make sure that that message is still here, remember, we disabled the endpoint on our data tier. We disabled activation. So this message is actually sitting in the transmission queue on one of my web front ends, waiting for that target service to wake up and start accepting new messages. Okay? So next up, what I'll do is I will start up the endpoint, and I'll enable activation. Now, the fact that we have the ability to suspend activation gives us a number of important capabilities. We can patch our activation stored procedure to do new things, as in the server log time case that I mentioned. The other thing that we have the ability to do is scale up activation. So I found the sweet spot, after a lot of experimentation, was about 20 threads on a dual processor, dual core system. Anything beyond 20 activation threads would kind of cause some problems. So that message has gone through, activation is fired, and we're now inside the SQL CLR procedure for the activation stored procedure in our data tier. So if I look at this, I made one simple deserialization call, and now I have a class that's fully populated with all the data that I need. For example, here's the client address name-value pair that came through. So I shredded it like that into a class. This CLR stored procedure then returns that as output parameters, and we just basically insert it into a table, and we're good to go. So if I come back here to Management Studio, we can check out the resulting row that showed up in our raw log table. We should have one row there, right? Now, at this point, I mentioned that we are running data refreshes at about a 5-minute interval. So I could spend all day just talking about this SSIS package. You talked about distributed transactions not scaling too well. I got bit by that. I re-engineered this package about 10 times to the point where we could handle massive volumes of data in the most efficient way possible. And there's a lot of tips and tricks in this thing that I just won't have time to talk about today. But one thing that I'll show you that was rather interesting you can see the package running here. In this load client addresses, there's a very heavyweight process where we geotag an IP address. We try to figure out what geography this IP address came from. The query for that is very expensive. So I do what I call a stupid mainframe trick down here at the bottom. You see the scale inserts? I check the row number. If it's even, I send it to one thread. If it's odd, I send it to the other thread. And now I've got 2 threads working on that very expensive geo-loading query. I could have done 4 of them, 6 of them, 8 of them if I wanted to. You know, just very, very simple things that you can do to improve the throughput of the system. So now that I've gone ahead and loaded up my data warehouse with my new log data, I can go back and take a look at the resulting data, and it should be geotagged based upon the IP address. So there's a client address for the request that came through, and it came from my desktop in Redmond. Okay? So this is the kind of transformation that was required in order for us to make this log information useful to do the types of diagnostic activities that we actually wanted to do. And just to kind of round this out, just to show you a few of our results very quickly, and then I'll wrap up. First of all, if you're interested in what healthy service broker activity looks like on 15 front-end web servers, that's it. That's a performance monitor collection of the number of messages dequeued per second on each of our 15 nodes. The one that is spiking, we had to patch, so it was catching up. So it had more messages to unload than the other ones, right? So this is just over like a 5-minute time frame, basically. So that's what a healthy service broker activity looks like. This is, unfortunately, I don't have time to actually show you the site, but the site was really compelling. How many of you actually used NBCOlympics.com? Great. So about half the room has already experienced the user experience that I was talking about, which is cool. So I guess the only other 2 things I want to quickly show you was some of the information that we got out of the system. Here's a reporting services report against our cube that talks about video starts. So this particular analysis service report shows kind of spikes in video start activity. That first spike that occurred around the 14th was the men's basketball finals. So we spiked at around 350,000 video starts in just that 1 hour for the live video feed for the men's basketball finals. And then you can see the closing ceremonies happening. Activity drops off just like next to nothing, right, after the men's basketball finals, and then the closing ceremonies kicked in. And a lot of people were watching live video feeds of the closing ceremonies. And that's the next set of spikes over the next several hours. So we were really able to get some pretty interesting usage-based information out of the system to help us understand how people were using it. And then
that probably reflects that the viewers were primarily from the U.S.
Yes, yes. It's a good point that Jose's making. I don't know if your mic was on when he said that, but NBC was trying to provide this service mainly to people in the U.S. They weren't interested in servicing Africa or Latin America or any of these other countries because they're trying to drive their ratings. So part of what we had to do was kind of like geofence things to keep international users from bogging down the system. So that was a big part of what the operations team at 30 Rock did. And then finally, if you look at this report, this is one of the really useful reports that we used for the operations team to help us understand what kind of activity was happening. And this was all relational reporting, okay? This was not a cube. And this basically, over a set of time slices, gave us a feel for what kind of events were happening. Video start events, excessive buffering events, add load failure events, right? And if we saw a spike, say, in excessive buffering, we had drill down reports on all of those things that would go against our relational data to go and figure out exactly what the nature was of those excessive buffering events. So that's the end-to-end kind of picture of the system. I hope it was useful to you, and I'll stick around for questions afterwards. Thanks a lot.
Thank you, Roy. Okay. So we now move to data partitioning and transactions. So the key idea here is we need, in order to be able to make data scale without limits, we need to define these units of data that are grouped together and that can be scoped to always reside in a node. And I'm using the term entity just for simplicity here to actually label this concept. Entities are identified by a globally unique ID, and they are scoped to preserve locality of transactions and operations on these entities. Okay? So, entities may span multiple tables, but if they do, then all the tables that contribute pieces to that entity must have that key or that ID, so that as you move rows around, as rows move in the presence of repartitions, all the elements of that entity move together to the same node. Okay? Now, entities migrate across nodes as a unit. So we talk about the entity as the unit of the scope of data that cannot be fragmented. Okay? This implies that the partitioning function that is applied to these entities must take that ID as an argument or be sort of like part of the equation of the partition function. Now, scalable applications and code can assume that the entities are local, all right? And they should never operate on more than one entity at a time. The reason for that is that while today a particular entity or particular group of entities may be living in a node, tomorrow they may be living in a different place. Okay? Now, every operation must work on an entity at a time, right? The whole purpose here is to guarantee locality. And there is no promise that two different entities will stay on the same node over time. So that's the whole key. If an operation or a transaction starts operating on more than one entity, without warning, at one point you are dealing with distributed or multi-node operations, and that particular activity is going to start ping-ponging and forcing requests across nodes, and that will become a bottleneck at some point. Now, locality is the key to unlimited scale. All right? So we talk about transactions updating a single entity and business operations working on single entities at a time. A transaction should never update more than two entities. All right? And we should try to minimize or avoid distributed transactions. Distributed transactions, while they work for limited cases, they are too brittle and at some point become your bottleneck. So now let's talk about how MySpace is using all of these design concepts. And Hala is going to tell us about how they have architected myspace.com to make the scale.
Hi, can you hear me? Yep. Okay. My name is Hala Adwan. I'm the Vice President of Data at MySpace. And I wanted to have a little talk. I'll try to get through it pretty fast because I think we're pretty close on time. But really to touch on the points that Jose brought up, which is scalability, partitioning, and messaging. So what is MySpace? MySpace is a social networking site like Friendster, like Facebook. It's just where people connect and are incredibly active. We do about 122 million active users a month, and our users are really active, not just from a read perspective, but also heavy writes. What are people doing? They're blogging, they're messaging, they're writing bulletins, they're commenting on people's photos, they're commenting on people's profiles. So there's a lot of activity going on all the time. They're uploading videos, they're watching videos, and so on and so forth. So there's a lot of data coming in, a high number of transactions going on all the time. Our storage footprint, our databases right now take up about 340 terabytes with a similar amount of backup snaps on our storage device.
Can I get your badge? Because it's robbing your
microphone. Okay. My microphone's on it. Can you still hear me? Yep. Okay. All right. More information about what we do at MySpace. We classify our database servers by type, and I'll go into that in a little more detail on the partitioning side. But you can see on average our profiles, which handle our user profile information, do about 600 to 800 connections per server. And our security cluster, which handles our login and sign up, does about 3,700 requests per second on that server on average. At peak, it's obviously higher. We use 3PAR as our storage device. We have about 6 3PAR frames. Each has about 1,120 disks in it. Our IOPS are, we do about 184,000 on average. At peak, we do 280,000. So there's a lot of activity going on all the time. So the MySpace system architecture. So at the heart of every system, there's web servers, and then there's persistent storage. And very early on, we realized that your web servers accessing your persistent storage is not a very good idea. There's latency involved in managing transactions and data and storing it. And we don't want to translate that latency to our users. So what we did pretty quickly was really come up with a 3-tier logical and sometimes physical architecture. So obviously, we have our web server tier, and we have our persistent data store. But in between that, we have a service layer, our API layer, that all the writes and reads go through. And then we have a cache. So most of our caching implementations are really writes coming in through the web server, data being directly written to our persistent data store, but the reads being served from cache. So what happens if there's a cache miss? It goes to the persistent data store, pulls that data, saves it in cache for the next time. So obviously, there's a failover component to our persistent storage, which isn't ideal. More recently, and over the past year, we've moved towards a pre-populator concept of cache. So the writes still go directly into our persistent data store, but we have a pre-populator component that takes that data and warms up cache and fills it with data. So now the assumption is that cache always has data in it, and if it's not in cache, the data doesn't exist. So there is no failover to the persistent data store. But there's still a latency involved in writes. So what we did was we built a transaction manager. It is a homegrown solution that really manages distributed asynchronous business messages. And it encapsulates the business logic in its payload, and it's actually able to manage the transactions across various persistent data stores. So if you have metadata and a media file, and you want to be able to manage a transaction around storing both of them, Transaction Manager handles that very gracefully. Of course, in certain cases, we can't really wait for the loop to go through because we want to be able to give the feedback to the end user pretty quickly. And in those cases, Transaction Manager will write to cache directly, and then in a lazy way, the pre-populator will backfill cache and make sure that all the data is clean and consistent. And finally, on the data side, on the database side, we also have a messaging infrastructure service dispatcher, which I'll get into in a little bit more detail, that handles messages between databases, and in certain cases will expose interfaces to the application into that messaging tier. So partitioning. Very early on, as our user base ramped up, we realized that there's no way we're going to be able to scale up, that really the only logical way for us to do this fast is to scale out. So we apply different kinds of partitioning at MySpace in the database tier. At the top level, we do functional partitioning. So what does that mean? We partition our user data into separate databases, and even within that, we have the profile data in specific databases and the messaging data in specific databases. Our feature, which is non-user-centric data, is partitioned in its own databases. And then we also have read-only databases that are partitioned in their own databases. What this allows us to do is, because each type of database has a very well-known behavior, we're able to tune at the server level, at the application level, and within the SQL Server Engine level. Within each of these functional partitions, we apply user partitioning. So our user data, we have hundreds and millions of user accounts. So what we do is we partition by million user ID ranges, incrementing. It's very simple. So as we add a new database for every new 100 million users. So you can imagine at our growth, which we have about 300, on average 300,000 new signups a day, that'll tell you how many databases we roll out every few days. In cases where we have feature databases that are very I/O intensive, and we know that one database isn't going to be able to handle the load, we'll partition our data across that by user ID as well, but we'll use a modulo in that case. And the modulo will depend on how I/O intensive it is. And then finally, within each database, we also apply table partitioning. Horizontal table partitioning, we call it the poor man's partitioning because we have over 1,100 databases. there's no way we can afford to run enterprise on all of them. So we run standard, SQL Server standard, and we have to do all of our partitioning logic in the stored procedures as opposed to leveraging the partitioning that SQL Server Enterprise provides. So we partition horizontally, but then also within those partitions, we'll partition vertically. So we'll partition horizontally on the key that is going to give us the maximum, most optimal reads. And then if there's blob data involved, we're actually vertically partitioned that. In each of those partitions, we'll split the tables up, vertically partition the blobs with an incrementing ID, and that way it's going to optimize our writes. So now we have 1,100 databases, and we violate Jose's rule of actually having a transaction write data to multiple databases. So how do we handle those transactions? With something we call Service Dispatcher. So handling those transactions was incredibly painful for us. And then SQL Server 2005 came out, and we were so excited because now there's asynchronous transactional communication between databases. And we rejoiced. And then we realized it's unicast messages. And we have 1,100 databases and growing. So what do we do? How do we actually leverage the power of Service Broker and not have to manage a route for every single database to every single database? So what we did was we came up with what we call internally Service Dispatcher. What Service Dispatcher is, it is considered like a router farm, or a set of database servers that route messages between all of our databases. So they abstract all the route management from all the endpoint or starter databases. We have a gateway in every single one of our databases and database servers that is aware of the routing system, of the Service Dispatcher system, and Service Dispatcher is aware of everything else. And so that way we just send messages to this dispatcher farm, and within the payload of that message, within the envelope, it knows exactly where to send it off to, and then we don't have to manage these routes everywhere. It obviously enabled us to do multicast messaging. And the other thing that it did is that we actually built abstraction stored procedures or APIs or whatever you want to call them in each one of those gateways that really abstracts all the complex components of Service Broker, such as dialogue management, from the end developer. So that way, when a developer wants to actually build something, it's just a matter of setting up a simple local service. So a very quick example of how a Service Dispatcher works is obviously you have an initiator database and you have a target database. So you have an initiator service and you have a target service. And then everywhere, there's a gateway. So the client initiator service talks directly into the gateway and says, hey, I have a message I want to send on. Within the envelope, I want you to send it to all the profile databases. And we actually support wildcard in our message destinations. That way, we don't have to be aware of every single profile database because we have hundreds of them. So we'll just say profile star, and then the dispatcher gateway will know where to send it off to. It sends it off to the actual dispatcher database, which is the router. The dispatcher database will open up the envelope, read the directions, know that it has to send it to every single profile database, and then sends it to the gateway services on each one of those databases, which then will send it back to the local target. So obviously, this is a very simple approach. If you think about it right now, this dispatcher infrastructure is so integral to our system that pretty much all of our back-end transaction management goes through it. Our code deployment goes through. If you think we have to deploy code to hundreds of profile databases, we use Dispatcher to enable us to do that. If you want to be able to manage, for example, a user wants to delete their account, their data exists in almost all of our databases. So we use that, this infrastructure to help manage the order of those deletes. And then if a user wants to restore their account, we go back and do that restore using the same infrastructure. The other thing that this provides is a feedback service. So when you send the message, you can request a receipt back. So that way, the initiator would get an acknowledgement from every single target that this message was received before it moves on to the next step if there's ordering involved. So again, very simplistic approach, but has been really key to us being able to cleanly manage transactions across our many, many, many databases. And again, I'm available afterwards if you guys have any questions about this.
Thank you very much, Ella. All right. So, summary. Talk about SQL Server Data Platform. Our intention, we are building a very comprehensive data platform to help you manage your data any place, any time, any scale. We're working hard to try to solve the majority of your problems, of your scale problems, automatically, okay? But there is this few percentage of applications, the really, really massively scale applications that require a special, careful design. So we talked about some of the patterns that we've used that have been successfully used in being able to build these kind of applications. Scalability is a problem of managing complexity. So to manage complexity, you have to divide and conquer the problem. And we talk about various partitioning, divide and conquering techniques, functional partitioning, data partitioning, making sure that your transactions and operations remain local. We talk about messaging. And these patterns were illustrated with 3 real-life applications. So hopefully you got a feel for what we're trying to do. Now, as we learn about these patterns, we try to codify them into the platform. So for example, for those, how many of you went to the SQL Services talk yesterday by Dave Campbell? Well, SQL Services is in some way codifying some of these patterns. I mean, they have the notion of a container or a table partitioning where you can define your entities to always live within that partitioning. And that, it's a limited scalability pattern in the sense that, or a limited database design pattern because it forces all the tables that in some sense contribute to building a particular entity must live in the same partition. But that's an example of how we are, as we learn about these unlimited scale patterns, we're trying to codify them in the platform. And we'll just be building and learning more and more of those patterns into SQL Server over time. This is a reminder to fill the evaluations for the recordings here. And at this point, we'll take questions.